So, in the alpha scattering experiment, when the alpha rays acted on the gold foil and they hit on the zinc sulfide wall, different kind of deflections were seen. So, firstly, some of the rays were undeflected, some were deflected at small angles, and some of them, like about 1 in 20,000 particles, deflected in higher angles. Like greater than 90 degree, and some of them also deflected in 180 degree. Some of them had higher angles. These were the observations of Rutherford alpha scattering experiment. So, what were the reasons? There were some conclusions in the Rutherford experiment. What were the conclusions? The first conclusion was most rays passed undeflected. So, this came to a point that most of the space in an atom are empty. So, this point was the first point to contradict Thomson's model, because in Thomson's model the atom had a uniform positive sphere and the electrons were also embedded in the atom uniformly. But when some of the rays deflected and some of the rays passed undeflected, then it was concluded that the most space in an atom is empty. So, no uniformity. This rejected Thomson's model. Now, the second conclusion was that few alpha particles were deflected at small angles. Okay, this can be due to the repulsive forces. So, in these observations, if some of them are passing through the gold foil undeflected, that would mean they had passed through some empty space. That is, they didn't have any barrier on their way, they didn't collide with any other particle. So, they could pass undeflected. So, the most of the space in atom is empty. But for some rays, they were deflected in certain angles. Why they were deflected? We know that like charges repel each other and opposite charges attract each other. We know that the alpha particles are ions of helium which have +2 charge, that is, alpha particles are positively charged. So, alpha particles must be repelled with some positive particles. So, it was again seen that some of the rays were deflected more and some of the rays were deflected less. So, it must have something to do with the distance between the alpha particles and the positive part of the atom. It can be concluded that when the alpha particles approached the positive part of the atom, that is the protons, then it deflected due to the repulsion of two like charges. Nearer the distance between the alpha particles and the protons, higher will be the degree of deflection. So, degree of deflection depended upon the distance between the alpha particles and the positive charge of atom, that is the protons. So, shorter distance between alpha particles and protons will cause higher degree of deflection. Okay, so from this conclusion, it was also thought that positive charge in an atom is located at a very small region. So, this statement also defied Thomson's plum pudding model. So, the third conclusion was some alpha particles bounced back, that is, they deflected at 180 degree, means they actually retraced the path. So, there must be some positively charged region where the alpha particles hit and they deflected straight back, retracing the path. So, that must be some head-on collision or direct collision. And Rutherford, by some measurements, he concluded that the nucleus, which is the region where positive charge is centered, the nucleus has a radius of around 10 to the power minus 15 meters, whereas the atom has a radius of 10 to the power minus 10 meters radius. So, you see, the nucleus is around 10 to the power 5 times smaller than the atom. You can easily compare this, like if you place a lemon or a very small ball in the middle of a big playground, that is the case with atoms and nucleus. So, the nucleus is very small as compared to the atom. Rutherford had provided models like this. If this is the nucleus and this is the atom, then when the alpha particles were passing far away from the nucleus, they passed undeflected. When they approached the nucleus, deflections occurred. First, they deflected in smaller angles. As close the alpha particle is to the nucleus, the deflections will be more. Some of the deflections were at angles greater than 90 degree, like this, and some collisions were just 180 degree opposite. This can be also understood by something like this. If you see the gold foil has these many atoms. So, when the rays are passing from distant from the atoms or distant from the nucleus, it will pass undeflected. Near the nucleus, it will be deflected like this, and when it passes through a nucleus, it will bounce back. So, from there the Rutherford model was generated. Rutherford's nuclear model of atom. Okay, so before discussing Rutherford's nuclear model of atom, there is another point that we need to discuss, that is known as distance of closest approach. So, what was the distance of closest approach? Consider the alpha particle of mass m, mass equal to m, and it is moving directly at the nucleus with a velocity v, okay, at any time. So, as alpha particle reaches the nucleus, velocity decreases. So, what will happen, that the alpha particles are approaching the nucleus. So, the alpha particles have a certain mass and a certain velocity. When they approach the nucleus, at first there was no force acting on them. So, they were approaching with a steady velocity. But when they approach the nucleus is positively charged and alpha particles are also positively charged. So, there will be a repulsive force. The nucleus will try to keep the alpha particles away from them. So, due to this repulsive force, the velocity of the alpha particles will decrease gradually, and at some point near the nucleus, the alpha particles will stop. So, the distance at which the movement of alpha particles will stop while approaching the nucleus, that is called the distance of closest approach. After that distance, alpha particles will not be able to approach the nucleus, rather they will deflect back, retracing their initial path. So, if this is the alpha particle and this is the nucleus. So, the alpha particle is moving like this, it is coming with a steady velocity. Suppose at this point the alpha particle stops. From here it cannot go any further, it will retrace back. So, this distance between the nucleus and the alpha particle is known as distance of closest approach, D. At this point V becomes 0. Alpha particle stops due to repulsion. We will next see its derivation. Thank you.